Okay, right. Welcome back here to another quick chemistry video. Today's topic is dimensional analysis. What is dimensional analysis? How we use it, the math of it. That's what we're going to look at here today. Sometimes people just call this problem solving. Ultimately, dimensional analysis in chemistry is how we really show our work. It's a certain way to set up your calculation, a certain way to set up your units, and it's a certain way to show your work in chemistry. So let's get right into it. Clearly here, before we can even sort of think about our dimensional analysis, we do need to talk a little bit about an equality. An equality is basically two things that represent the same amount of something but are on different scales. So, very simple example, 12 inches equals 1 foot. 1 pound equals 453.6 grams. 1 inch equals 2.54 centimeters. 1 gallon is equal to 4 quarts. Each one of these is an equality. They represent basically the same amount. For example, the same length, the same mass, also length, volume as well. They're on different scales, but they both represent the same thing. Clearly, if you had 100 pennies, that would equal $1. Now, when we have an equality from any of these equalities here that we see on the screen, or really any equality that you come across, you could write another really important part of dimensional analysis, which are conversion factors. And conversion factors, frankly, they're just fractions. So if we take the top one there, we take 12 inches over 1 foot. One of our values is the numerator on top, and one's the denominator on the bottom. That gives us one conversion factor. We could get two by simply just flip their position, right? So one on the bottom goes to the top, and the guy on the top goes to the bottom. And now we have not one, but we basically have two conversion factors available to us. We could do it for anybody. We could do it for this guy here. We could go 1 pound over 453.6 grams, are up on top 453.6 grams over 1 pound. Again, two conversion factors from one equality. Now, will you use both of these conversion factors in the same problem, in the same calculation? I would bet against it, because if you know anything about fractions, and as we'll talk about in dimensional analysis, you essentially cancel each other out if you use this conversion factor and this conversion factor together in the same dimensional analysis sort of setup. Is pretty much going to cancel each other out. Why is that, you're saying? Let's talk about really the idea of dimensional analysis, how to set it up, what we're doing with the math part of it, and how that all works. So the idea of dimensional analysis is it is basically unit based. And in dimensional analysis, we use a series of fractions to get rid of essentially the units we don't want and end with the units that we do want. It is a super simple concept that a lot of people have a lot of trouble with because they think it's really more complicated than it is. So what do we have to remember? Pretty much this: opposites cancel. And if you put things in the opposite location, and the things we're talking about are pretty much units, if you put the units you don't want in opposite locations, they're going to cancel out. So for example, if we had unit A and we eventually wanted to get to unit C, for example, and we had a couple of qualities that would allow us to do that. Let's just say that we had unit A is equal to unit B, and unit B is equal to unit C. So these are our equalities. And again, from each of these equalities, we could generate two conversion factors. So in this case, we could say unit A over unit B, or again, our other fraction, unit B up on top, over unit A. From this guy here, again, we could get two conversion factors, unit B over unit C, or again, we just simply flip it around, unit C over unit B. So if we were going to go do a problem here, what you first want to think about when you're doing a dimensional analysis is, how can I go from here to here? Maybe a direct conversion, may take a couple of steps. So if I just think about my equalities, the pathway that will allow me to get to where I need is, I could go from unit A to unit B first. And once I'm in unit B, I could then go from unit B to unit C in a second step. So how do we set this up to show dimensional analysis and show how it works? So in this example here, we're going to do a unit A to start with, which is sort of what was given to us. So if we think about that, that right there is what is given. And now this is a second really important idea of dimensional analysis, which is it's fraction based. So what does that mean? When I write a number like this, unit A, it is technically speaking, although most people never write it like this, it is basically a fraction. It is basically over 1. Why is that important? It allows you to visually see two really important parts of your calculation. There's frankly a top part, guy up on top, and there's a bottom part on the bottom, obviously. And that's really important for our major concept of opposites cancel. So when I set this up, I'm going to now use a conversion factor. I personally like to put parentheses around it. Some people like to do, some people call it like a railroad type of ties thing where they just kind of use kind of lines to go between things. I like parentheses. You can use the line method if you like as well. It's all the same. So here we go. We're going to take our first step here using our first equality and our two conversion factors. We do not want to use both of them. We want to use whichever one's going to allow us to get rid of unit A. We don't want unit A anymore. So unit A is on top. That means to get rid of it, opposites cancel. I need unit A in the opposite location, which is on the bottom. And that's the conversion factor here on the right. So that is unit A on the bottom and unit B up on top. This is going to allow, in this case, unit A to cancel itself out. You may say, how does it do that? It's a good question. So at this point, let's talk a little bit about the math. When we set up dimensional analysis, we're essentially only doing two math operations. We're either going to multiply or divide. How do you know which one you should do? Also very simple. Whatever's up on top gets multiplied. Whatever's on the bottom gets divided always. So anything on top gets multiplied, anything on the bottom gets divided. That means unit A up on top will cancel out unit A on the bottom. Again, you may be saying to yourself, how does that work? Well, Essentially, we're going to be taking unit A that's up on top and divided by unit A that's on the bottom. Those two are going to cancel out and basically equal 1. Real life example, if I divide 2 by 2, and that's going to equal 1. Divide 4 by 4, and that's also going to equal 1. So if I have the same unit on top as I have on the bottom, they essentially cancel each other out because they basically equal 1. So what I'm left with at this point is now unit B. Now the benefit here of setting it up like this is unit B is clearly still up on top. And that's going to help me when I come to my next step, which is I need to get rid of unit B. So I need to put it in the opposite location. And that's going to be the conversion factor here on the right. I'm going to continue on here. You could get an answer if you wanted to, but the beauty of dimensional analysis is you don't really need to. You could kind of just continue on in this case. So unit B is up on top. Unit B here, my conversion factor is on the bottom. I'm going to put it in just like so. Unit B on bottom. Unit C on top. Again, we're going to continue to multiply what's on top. And we're going to continue to divide whatever's on the bottom. That means ultimately we're dividing unit B on top with unit B on the bottom. Once again, going to equal 1 and cancel out. That at this point in my calculation is going to leave me unit C. And that is the unit I am looking for. So math-wise, what we're doing is when we set it up like this, everybody on top gets multiplied. Then you come back, whatever numbers you got on the bottom, we divide. So now we kind of use the generic sort of guys. Let's get into perhaps something with some real conversion factors and some real numbers. So let's take a look at our 1 pound is equal to 453.6 grams. Once again, that's our equality. From that, as we talked about earlier, we could get 1 pound over 453.6 grams. Or flipping it around, 453.6 grams over 1 pound. Again, these are our conversion factors. All right, so let's just say that we had, I don't know, let's go with a nice made up number of 32.5 grams. And we want to know how many pounds that would be. So again, we're going to start with what was given to us. 32.5 grams. Again, not really written as a fraction, but if it helps you visualize top and bottom, which is important for dimensional analysis, just throw a 1 on the bottom. Now, again, we can see this guy's up on top. This guy's on the bottom. We're ready to do our conversion. So I know I want to get rid of grams and end up in pounds. This is actually a direct conversion that's going to allow me to do that. So what do I have to remember? Opposites. I got grams on top. Should I use the one here on the right? The answer is no, you don't want to use the one on the right. Pounds are on the bottom. That's not going to work. You want to use the one on the left. Grams are on the bottom. Grams are on top over here. Opposite to get rid of them. Grams goes on the bottom right about there. And up on top, 1 pound. Once again, we're going to multiply what's on top and come back and divide by what's on the bottom. Unit-wise, grams will cancel. Going to leave you the only unit left, which is a pound up on top. Put a little 1 there so it don't look like 11. So again, we're basically taking 32.5 times 1, which you don't really need to do, divided by 453.6. And that's going to give us on our calculator here 0.0716. I'm going to just write all the numbers here. 4903. The units are grams. This also brings up a really important thing that we talked about in a previous video about significant figures and calculations. Perhaps I'll put a little link to it right now in case you haven't seen that video. But we do want to give our answers usually to the right number of significant figures. This right here, like a lot of conversion factors, is considered a number where you do have to look at significant figures. Some people will consider it's an exact number, but it's really not, because it's kind of like 453.59, I think is the real number. So we should look at the sig figs here in this particular case, and this has 4 significant figures. Our original number here has 3 significant figures. And we're looking at significant figures because the nice thing about dimensional analysis is you're going to always look at significant figures because we are only multiplying and dividing. That means we probably should end about 3 sig figs, which is right about there. And we'll end up with 0.0716 grams. Now, in this case, you probably should look at significant figures here, as it is a metric to English conversion. And those are typically not considered exact numbers. There are a few metric to English conversions, like, for example, 1 inch is 2.54 centimeters. That is considered an exact conversion. But most metric to English, or sometimes people call it US units, are not exact numbers, which means when you use a conversion factor that comes from those, you do need to take into account the significant figures. What significant figures should you take into account? Well, a lot of times one of the values will be a 1, so you shouldn't look at that. You should look at the other number in those type of conversions that is not 1. Now, what about if you're using a metric to metric, or English to English conversions? Those guys are considered exact numbers. And a reminder that exact numbers pretty much could have an unlimited number of significant figures, which means when you're doing calculations like this, when you're multiplying or dividing, you're not going to worry at all about their contribution to your answer in terms of significant figures. So I would say probably 9 times out of 10, maybe even a little more, if you're using a conversion factor and you're just doing a dimensional analysis problem, it's probably going to be an exact number. You don't have to worry about the sig figs of those conversion factors, which means 9 times out of 10, kind of the first number you start with in your conversion or dimensional analysis problem oftentimes will have the correct number of significant figures. Not all the time, but a lot of times it will. You really only have to worry about this situation here. When you cross over, these are usually not considered exact numbers, and you do need to take those into account in terms of your answer in significant figures when you cross over kind of that metric to English conversion. So how can we do this if we got multiple units that maybe we want to get rid of? Let's just say that we were driving 45.5 miles per hour. And we want to know maybe how many kilometers per second that was. Well, how do we do that when we got multiple units going? Well, first off, when we see miles per hour, that's basically 45.5 miles over an hour. And that's basically what the per means. It's a fraction. You got actually 2 units going on here. What do we want to end up with? We also got 2 units going on, kilometers over a second. So we want to figure out in our sort of setup here how we get to kilometers per second. We want a pathway basically on top that takes us to kilometers. We want a pathway on the bottom that takes us to seconds, essentially. We are setting this up, and you can even see the way I wrote those fractions, kind of dimensional analysis way, top and bottom clearly labeled up there. Basically, you could clearly see miles are on top, hours are on the bottom, kilometers are on top, seconds are on the bottom. Now, when we do conversion factors like this in dimensional analysis, there are more than one way that you could get to your answer, depending on what conversions you choose. There may be a direct route to your conversions. There may be multiple conversions needed to get you from one unit to the next. As long as you choose legitimate conversion factors and equalities, pretty much you can sometimes get to the same answer using different conversion factors. So as long as they're legit, you can do that. For example, one equality is 1 kilometer is equal to 0.621 miles. That's an equality that will actually directly take us from miles to kilometers. Now, hours to seconds. Well, we hopefully know 1 hour. There are 60 minutes, and we know hopefully in 1 minute there are 60 seconds, right? So again, these are a few equalities that we can use to get us to where we want to end up. We know that for the first one there, 1 kilometer over 0.621 miles are 0.621 miles over 1 kilometer. This would be the two conversion factors for our top equality. Obviously here we would have 1 hour over 60 minutes. Or we again could flip it around, 60 minutes over 1 hour. And lastly, squeeze it in right about there, I think. 1 minute over 60 seconds are 60 seconds over 1 minute. And I did write SEC for seconds. I could just write S, which might grab my eraser here and maybe do that. Actually, what I'll do, that way I'll kind of be consistent in terms of the units I'm using here for seconds. There we go. So seconds and seconds. There we go. All right. So you can see here our pathway. We actually have 6 conversion factors that we could use. We're not going to use all 6. We're just going to use the ones that we need. So in this case, we have 2 sets of units. And again, it's super important to start it out like I wrote it there. 45.5 miles over an hour. And again, the purpose of setting up like this is I know what unit's on top and what unit is on the bottom. Doesn't matter which one you start with. And what I mean by that, it doesn't matter if you convert the miles first to kilometers or you convert the hours to seconds. It doesn't matter. I'm going to start with miles and take it to kilometers. So once again, my pathway here is I could go from miles to kilometers. That is going to give me an option from that equality of 2 conversion factors. Oh no, which one should I choose? Remember, your friend is opposites. That's cancel. Opposites cancel. So miles are on top. That makes the decision super easy for me. That is the conversion factor where miles is in the opposite location, which is the unit I want to get rid of. So I will put it on the bottom, and up on top would go 1 kilometer. Once again, if we stop the calculation at this point, math-wise, a reminder that we are multiplying what's on top and dividing by what's on the bottom. So ultimately, unit-wise, miles gets divided by miles, and they now cancel. If I stop the calculation right at this point, the units that I have are kilometers on top, hours there on the bottom. That is good because I am halfway to what I need. So the beauty of this setup is, although I'm in kilometers per hour, I've now converted the top part correctly. And now I'm ready to do the bottom part. And the nice thing about it is, again, coming back here, I could clearly see The hours are on the bottom. So once again, opposites. So here we want to get rid of hours. So we're going to take our conversion from hours to minutes using our equality here. And again, we have two options. We have this guy here on the left, this guy here on the right. Well, kilometers are on top. So what should I do? There it is, opposites. Kilometers on top. We want it there. Hours are on the bottom. We want to get rid of hours. So since hours are on the bottom, I need hours in the opposite location there. And that's going to take that conversion factor right there. 1 hour on top, 60 minutes on the bottom. Hour on top divided by hour on the bottom. They cancel those units. And again, we are multiplying this guy and we're dividing this guy. If I stop the calculation right at this point, up on top is kilometers, which is what I'm looking for. And now on the bottom is minutes. Getting closer to what I'm looking for, which is seconds. That means I do need to do one more conversion here. And again, setting it up like this, I could clearly see my minutes are on the bottom and I want to get rid of that. So I need minutes up on top, and using our conversion factor, which happens to be right above it, we are going to use the guy there on the left and put our 1 minute up on top and our 60 seconds on the bottom. Again, we're going to multiply and divide here. Minutes on the bottom, minutes on the top will cancel. And now I am left with seconds, which is what I want. And it's actually in the right location. I kind of clean it up here a little bit with the eraser. Trying to get rid of this conversion factor out of the way here. It's got a little tight in there. Oh. So now we actually have the units that we want. We are ready to actually do the math. So we're going to grab our calculator. Got one laying around here. I think we're basically again going to multiply everything on top. So in this case, that's 45.5 times basically all ones up there. If you want to multiply, you can, but you really don't need to. 1 times 1 times 1. Really important when you set up these things for dimensional analysis. You can multiply as many numbers as you got up on top. At the end of that, make sure you hit your equal sign on your calculator. So you can hit equals. Obviously, in this case, you got 45.5. The next thing people always mess up on when they go punch in their calculator is the bottom part. They want to punch it all in at once. So how should we do it? My advice is this: if you got multiple numbers like we do here on the bottom that needs to be divided, not multiplied, but divided there on the bottom, you should do each one individually. So what do I mean by that? I took 45.5 and I hit equals up on top after I multiplied everything. I'm now going to do this. I can type the calculator sort of move. I'm going to hit the divide button. And I'm going to divide it by the first number there, which is 0.621. And then I'm going to hit the equals button on my calculator. I am then going to divide it by the next number on the bottom, which is 60. So I'm going to then hit on my calculator the divide button and type in 60. And then I'm going to hit equals. And I got one more number on the bottom there. I am again going to hit the divide button and divide it by 60 and hit equals one more time. When you have multiple things on the bottom, you definitely want to hit that equal sign. Every time you divide by one number at a time, you'll always get the right answer. If you try to put all that in at once, if you don't put parentheses correctly, you're going to get the wrong answer most of the time. So I see it a lot. Happens a lot with people try to put a bunch of things in at once in their calculator, never gets the right answer. If you have multiple things on the bottom, divide by the first thing, hit equals, divide by the next one, hit equals, divide by the next one, hit equals. However many you have, you will always get the right answer if you basically take that approach. And I would highly recommend that you do that. So when we do that and put it into our calculator correctly, we will end up with a number here on our calculator of 0 point, right here actually, 0, get my 0 there, pretty bad looking 0, 0 0.020352478. This is the number you see on your calculator. By the way, the units here are kilometers up on top, which the number stays with it, per second. Where should we end up with our answer? We do need to look at significant figures because we are multiplying and then we're dividing basically. So that is all significant figures all day when we're looking for our answer here. So this is considered an exact number, so we don't have to worry about it in terms of significant figures. 1 hour, 60 minutes, also considered an exact number, so we're not going to worry about it. That's a metric to English conversion, which means we should look at the sig figs here. And that number is the one we want to look at. That has 3 significant figures. We do not want to look at the 1. So that was what I was talking about earlier. In a metric to English conversion, a lot of times you'll have a 1 as one part of the conversion factor. You don't worry about that one. You look at the other number, in this case, the 0.621 has 3 significant figures. Our original number here, 3 significant figures. So that's going to bring us here. That's a 5. That's a rounding situation. Going to get us a 0.0204 kilometers, stays with the number up on top, and seconds on the bottom. So this is a really good example of multiple units handled very simply by dimensional analysis, keeping a top unit and a bottom unit, and things work out really well. Can't tell you how many times people would do this problem and not set up dimensional analysis where they could see the units canceling. And in the end, instead of dividing by the 60 on the bottom there and the 60 on the bottom, they will end up multiplying by those things. And that happens a lot of times when people just kind of write units like this, miles, hours, kilometers, miles. They're not really sure what's on top, what's on the bottom. They're not really sure, should I multiply? Should I divide? They're not really sure. So the beauty of dimensional analysis is, doesn't matter how many conversion factors you use, whatever number you're starting with, which is starting up on top, all you have to remember is whatever is on top, as many of them as I got, I'm multiplying. And whatever is on the bottom, as many as I got, I'm dividing. Keeps it super simple. Just remember those 3 things basically. Opposites cancel. If it's on top, you multiply. If it's on the bottom, you divide. And the benefit of dimensional analysis is this. You could do a lot of problems in chemistry using dimensional analysis. And just by thinking about units and how to cancel out units correctly, you oftentimes can just use dimensional analysis and sometimes not even have to worry about remembering chemistry formulas, because the dimensional analysis will take care of the math for you. And by taking care of the math, it will oftentimes take care of rearranging equations. For example, if you had density and you were given a density of something, like the density was 1.32 grams per milliliter, you could just turn that thing into a conversion factor of the density, 1.32 grams over milliliters. Or you could flip it around, a milliliter is 1.32 grams. Now, for example, let's just say you had 12 milliliters of this solution. You want to know how many grams that could be. Right. So obviously density is mass divided by volume. And if you want mass is equal to volume times density. So you could use the equation if you knew it. But let's just say, for example, you didn't know the equation, couldn't remember it, having a bad day, whatever it may be. You could take a dimensional analysis approach and go, okay, I got milliliters, I need to get to grams. It gave me this kind of conversion factor that I could use as a conversion factor. Let me see if I could do that. Well, I got 12 milliliters. I'm going to set it up dimensional analysis. What do I have to remember? Oh yeah, opposites cancel. So milliliters are on top. I'm going to need milliliters on the bottom, which should be this conversion factor here. 1.32 grams on top, milliliter on the bottom. What do I do for math? Oh, top, multiply. Seems good. Bottom, divide. So I'm going to multiply basically in this case my 12 times 1.32, hit equals. I can come back. Remember, if there's nothing written next to the unit, it's assumed to be 1. So we basically just got ones on the bottom. So if we divide it by 1, we end up with 15.84 milliliters on top. Canceled, leaves me grams. And obviously sig fig wise, we got 3 sig figs there and 2 sig figs there. We're multiplying, dividing. So 2 sig figs looks like 16 grams. Feel like I just rearranged that equation without even using the equation. And that is the beauty of dimensional analysis, is it can allow you to essentially rearrange equations without even actually using the equation. So it's really important to set things up this way in chemistry. And it's really kind of 3 simple things to remember. If I want to get rid of the units, go opposite. Whether they're on the bottom or top, I just need to go opposite to get rid of those units. I want to keep whatever units I'm looking for. I multiply everything that's on top. I divide everything that's on the bottom. And that is the simple approach to dimensional analysis. You want to make sure that you set it up that way. It makes the math easier for you. It makes sometimes not having to remember formulas a lot easier for you as well. I would say just remember this as well. If you're looking for just one unit at the end, that unit usually has to be up on top and by itself to be the correct unit. And if you have 2 units like we did in this last example, just keep the top and bottom units separate and treat them separately and go opposites to cancel them. There's a quick look, hopefully, at dimensional analysis. Not sure how quick it turned out to be, but I hope it enjoyed this little mini sort of lecture here on dimensional analysis. If there's any other chemistry topics you'd like me to look at or sort of make a small video on, let me know in the comments. Otherwise, we'll see you on the next one. Thanks for watching. Have a good one. Bye-bye.